Hey guys, today we're going to focus on data analysis of variance. So we're going to look at comparing multiple groups for a dependent variable. Let's get started. Marketers find themselves in a regular situation where they need to compare multiple groups. It might be user groups, light user groups, medium user groups, heavy user groups for their brand, and see how they compare on variables such as satisfaction or likelihood to purchase. So the statistical test we'll use is analysis of variance, and we'll explain this here just in a minute here, but it becomes very useful for marketers. So our null hypothesis here in an analysis of variance test is that all the subgroup means are equal. All the subgroup means are equal. So the population subgroup mean mu1 is equal to mu2 is equal to mu3. And so this is the way we'll do it with sum of squares computations, and we'll show you that here as we get going here. So really what we're going to compare is, the how much spread in the data is there across the groups with the main, how much of a spread in the data is there overall, I guess, with the overall mean and each of the respondents, and then the spread in the data across each of the groups. So that's what our approach is here, and might be for in-store promotions here. That's our X variable, and then the sales is Y. So our grouping variable is in-store promotions. Here we see a graphical depiction of this. Sales is on the left. We got low in-store promotions here. We got medium in-store promotions and then high in-store promotions. So it looks like there is a linear relationship here across these groups, but analysis of variance will assess whether there is at a statistically significant level. So here are the relative ratings for in-store promotions here. We got the high in-store promotion group. We have 10 stores here in this group, and they range from 10, 9, 10, and 8. And then that has an overall subgroup mean of 8.3. And then our medium in-store sales, the sales here has a mean value of 6.2 for sales for that medium in-store promotion group. And then for our low in-store promotion group, we have 10 stores, and that has a value of 3.7. So these are key means for us. The subgroup means here for high, medium, and low in-store promotions, 8.3, 6.2, 3.7. And then our overall mean here, our grand mean, which is 6.067. Okay, so we'll start with 6.067, our grand mean in our computations first. So to compute the sum of squares of Y, we'll take that first respondent, that first store in the high in-store promotion group. It has a rating of 10 for sales, and then we're going to subtract the grand mean, the overall mean for all of the stores, 6.07 from that. Then we're going to square it. Okay, and then we're going to go to the next value, 9, subtract the grand mean. We're going to square that difference. And then we're going to go to the next one, 10, subtracts the grand mean, 6.07, square that. And then we're going and making this computation of difference with the grand mean, squaring it, and we're summing. So here we get these differences here, and then we're squaring them. And the total of all these squared differences is 185.867. Okay, our sum of square X here is computed this way, that we have the sum of square errors term, 10 minus 8.3, that's that subgroup mean for the high in-store sales promotions. And then we go to 9 minus that subgroup mean, square that difference, 10 minus 8.3 to subgroup mean, go back to 8 minus 8.3, square it. And so we're getting down here to our square terms, we're summing that. So we got 79.80 for sum of square errors, So here our sum of squares y was computed initially as 185.867. You compute the sum of square errors, then the residual term here is 106.067. To get this eta square relationship, to understand what our relationship of S of x, sum of squares x to sum of squares y, get 106.067 divided by 185.867, and that's 0.571. So in other words, 57.1% of the variation in sales, or y variable, is accounted for by in-store promotion, that grouping variable x, and it's a modest effect. So when we go here to our F statistic that we would compute for a analysis of variance, put our S sum of square x term here divided by the denominator, which is the number of groups minus 1. So we had 3 groups minus 1, that would be 2. And then we have the sum of square errors term here, which is 79.80 divided by the total sample. That'd be 30 minus the number of groups, which was 3. That'd be 27. So we get to this mean S of x and then this mean S of error. And we get this relationship here, 106.067 divided by 2, and then divided by 79.8 divided by 27. And this gives us this F statistic of 17.944. All right, so when we go to a statistical software program like SPSS, could be JUMP, JMP, could be SAS, SAS, could be Excel, that we get a F table such as this. Okay, so we see our sum of squares for our grouping variable, sum of square error term here, then our sum of squares y, our mean square here, and then our, which is really this term divided by the degrees of freedom, that gives us 53.03. 79.8 divided by 27, that gives us 2.96. And then we're going to divide this. We have a ratio of 53.03 to 2.96. That gives us our F ratio of 17.94. And when we go to the tables for F distribution, we see that F ratio puts us way out in the right side, which is of that distribution, which is in the reject region. So we would reject. So this p-value is less than 0.05, which is our threshold value for making a decision about our test statistic, or H sub 1, our alternative hypothesis. So there is, you would reject the null hypothesis that all the group means are equal. They're not, according to our F statistic here in our analysis of variance. And so we are in the position of saying, no, not all of these means are the same, and some of them are bigger than others. Okay, some of the assumptions for analysis of variance. These categories for our groups need to be fixed, so they can't be overlapping. Your error term is normally distributed and uncorrelated if you have only one person making a response or one store, and it doesn't appear more than once in your data set. So with that assumption, your error term is going to be normally distributed and the error terms will not be correlated. And so we are all about this F ratio here, the variance between groups, and how does that compare to the variance within the groups, okay? And so the Santa Fe Grill owners, they want to know if there's a difference in the likelihood of returning to the restaurant based on how far customers live from the store. All right, so here is our 3 categories of distance from the store: less than 1 mile, 1 to 5 miles, more than 5 miles. We see the means here, 4.91 in terms of likelihood to return, 4.63, 4.01 here for more than 5 miles. Is that statistically significant? We go to our analysis of variance here. We compute our sums of squares within groups, our sums of square y. We do our ratios here, and then we get this 29.3 to 1.08. That gives us an F value of 27.163, and that is far out in the F distribution to the right, so it's beyond the 0.05 level of that distribution, and so we would reject the null hypothesis that these 3 groups are this same on their likelihood to return. So it looks like if you live closer, you're more likely to return. So a weakness of analysis of variance is that the test does not specify which pairs of mean are different. So follow-up tests can be done. You can do this in these software programs. One of these tests is the Ch11b procedure. There are others like the Tukey that you can do too. And so here, when we run this Ch11b test here, our outputs look this way. So we're comparing to less than 1 mile group, and then compare that to the 1 to 5 mile group. And then also our more than 5 mile group here, we see the difference here is 2.77 and then 0.893. There's a star there, meaning the difference is significant at the 0.05 level. We see that here in our significance for that test, 0.00. When we get the moderate group compared to the other two, we see that the moderate group, 1 to 5 miles, is statistically significant beyond the 0.05 level for that difference. And then more than 5 miles, it's just the reverse of what we've seen previously. So those are statistically significant tests here. So there are differences, and we can see that particularly that more than 5 miles group is different than the other groups. Analysis of variance can be more than one way. So you can have more than one grouping variable. So this would be, if you had 2 grouping variables, you'd have a 2-way ANOVA. Okay, and so now you can have an interaction effect between these 2 grouping variables. Here's an example from marketing. This is real data from the Mary Kay Corporation based in Dallas. It's a direct selling organization for cosmetics and been highly successful over the years. So can you make out the young guns effect here? So what we see here is that we have number of, I guess the level of tenure here are the lines we have. So the blue line here is for the young, or 0 to 3 years in tenure. So these are the young guns. And then our green group here is 4 to 8. Okay, and then we have 9 to 15 years, 16 and above. So it looks like those terms here are a little more even than the young guns here. So we can see that there's this crossover effect. So particularly for the amounts of wholesale goods that are sold by these salespeople, that when you get up to the large amounts, that's accounted for by the new customers, the new salespeople, and also with regards to new customers. So they're the ones that are racking up the new customers and the new sales. So finding and recruiting these new salespeople is important to Mary Kay. You can see that the salespeople here, they do eclipse or overcome the directors, who are the more veteran salespeople in the organization for those big sales and the number of customers. So finding those dynamic, effective, young salespeople is important to the Mary Kay Corporation. And you can see it graphically depicted here in the results here. So there is this interaction effect here, that there is a interaction effect between, I guess, years as a salesperson and the success, the amount of wholesale amounts for these people. And the dependent variable here would be number of new customers. So you can have actually in ANOVA, you can have 3 grouping variables, 4, and this gets complex. You'd have to have strong theory or reasons to have such an effect when you have complexity in these relationships. But the in-way ANOVAs are out there and can be done, in structure and relationships in the field. So here we have an in-way test here. We have a 2-way ANOVA. We got the, I guess, the 3 groups here, and then we have the gender. So we're trying to see if there's an interaction effect between your distance from the restaurant and gender and likelihood to recommend to others. And so we go down here to these, our lines. X30 is the distance. So there is a main effect here. There is a main effect for gender. Okay, so one of the gender groups is higher than the other. And then this is the interaction term here. the distance by the gender effect. So when we go here, we see that the F statistic is small, and so the significance level associated with that is higher than 0.05. So we would retain our null hypothesis that there is no interaction effect between just distance driven to the restaurant and gender. We can also do perceptual mapping from some of our survey results or rankings. Here we see an example of ratings of 6 fast food restaurants on food freshness and food temperature. So McDonald's and Burger King looks like they're lower here on food freshness, and also on food temperature, they're kind of moderately related there for food temperature. So when we plot these, so this is food freshness dimension, left to right, we see that McDonald's and Burger King are coming in here just above 2, and then at food temperature, they fare a little bit better. That's the y-axis here. And we can see that Backyard Burgers and Wendy's are more favorable on high food freshness and high food temperature. So if we wanted to improve things here for McDonald's, perhaps we would get rid of that oven lamp and the rack for placing burgers there after they're coming off the grill to be heated. No, they would just be custom made and be directly moved to the bag and served to the customer. If we did that, that's more like what's happening at Wendy's and Backyard Burgers, and the perception for this restaurant would go up. So that's an operational change that could be done here for McDonald's and Burger King. For Burger King, they have flame broiled burgers. I don't think they have a warming rack, so their advertising could emphasize that when they come off the flame grill, they go into a bag and they're given to you just like you want them, and that way freshness of food perception would go up here. So that can be done through advertising. So that's a way marketers can use these results from perceptual mapping to guide them in making operational changes and advertising changes as well. So perceptual mapping is used for new product development. So looking at the gaps there and where you can move and place your new innovation in a positioning scheme, image measurements, advertising like we just discussed, all that's possible. So the multiple groups are important to marketers, and thank you for being with us today.